Okay, I think we can start. So Alexandre Krajenbrink is going to talk about the classical integrable structure in the weak noise theory of the KPZ class.
Thank you, Guillaume. Hi, everyone. Thanks for being here today. So as Guillaume just mentioned, I want to discuss with you today the classical integrable structure in the weak noise theory of models in the KPZ class. I'll give a fairly long introduction and enter into the mathematical details later on. So to kind of set up the scene, today I want to discuss the weak noise theory, but what does it mean? The weak noise theory describes the dynamics of the models in the KPZ class in the instance where we have tuned the variance of the noise or the randomness to be small compared to units of the systems. So in the weak noise theory, the variance of the noise is small compared to the units of the system. So the systems are almost deterministic. And because the system is almost deterministic, we'll try to condition it to be far away from the typical value or the expectation value of the dynamics. And because we'll force the dynamics to be far from its typical value, we'll have a large deviation principle. And the goal will be to try to characterize the large deviation principle and try to obtain some large deviation rate function, for instance. Historically, there's been two methods to try to characterize the weak noise theory of the KPZ models. The first method was to study the Freedom determinants that were obtained to characterize exact solutions of models in the KPZ class. So Freedom determinants appearing in the KPZ model for polymer models or for the q-TASEP or other type of models. And from those Freedom determinants, one could apply some asymptotic analysis to try to get a large deviation rate function. So this was one method. The second method is actually kind of orthogonal, amounts to study the dynamics using a variational approach, and the variational approach kind of leads to a system of nonlinear differential equation, some kind of hydrodynamic approach to those large deviations. And each method had its pros and cons. So the pros of the first method using the Freedom determinants was that we could get fairly easily the entire large deviation rate function. The cons is that the Freedom determinant is only available in the KPZ class for a handful of initial conditions, so it is extremely limited, it's extremely restricted. The second method, on the other hand, is fairly general in the sense that we can have a set of hydrodynamic equation, whatever initial condition we have for the system. The problem was that people could study the solution of those nonlinear equations only approximately to obtain the cumulants or only asymptotically to obtain the far tails, but no one could really obtain any exact solutions with those equations. So this has been really frustrating. It's like going to a wine and cheese and the host tells you that you can only have the wine or the cheese, but not both. And it's taking a few years, but actually we did try to combine the best of the two worlds, try to have a description that is fairly generic for all initial conditions, and at the same time try to obtain exactly the large deviation rate function. So there were some pros and cons. Which we've tried to solve over the course of a couple of years. And the holy grail of studying the weak noise theory was actually to try to obtain exact results, integrals or results that you could write down, and I'm going to describe this to you later on. And we've been able actually to reconcile these two methods a few years ago with Pierre, who's in the audience today, by realizing that the nonlinear differential equations that appear with the second methods in the second method are actually integrable in the classical sense. So if they are integrable, they can have a Lax pair formulation, and if they have a Lax pair formulation, then you can employ the scattering methods using the direct and inverse scattering methods. So we have realized that the hydrodynamic equations are integrable in the last sense. And it took us a few years to realize this, but when you think of it, it's a bit like the duck test that Percy Dave mentions all the time. I had to write the citation down, but basically it says that if it looks like a duck, swims like a duck, and quacks like a duck, then it probably is a duck. So we know those whole theories, like the q-TASEP, KPZ, O'Connell, they're all integrable. So maybe a sub-theory of those theories should also be integrable. So maybe in hindsight, after a couple of years, it doesn't really come as a surprise that this weak noise theory is integrable, but it took us a lot of time to actually realize this. And today I'll kind of dig rather in the second method, so try to define this weak noise theory in terms of a hydrodynamic system. And the philosophy behind this will be to approach a problem using a field theoretical approach that is rather a physicist type of approach, even though I'll try to describe whenever this approach is exact and partly rigorous. So the basis for the second approach, we'll use field theory and the Martin-Singer-Rose approach, or the MSR formalism. So we'll describe the stochastic dynamics as some kind of with an action, and the weak noise theory will consist in taking some form of saddle point of this action, and I'll describe in which regime we can actually have a saddle point formulation of the theory. And the saddle point will lead to a set of nonlinear equations. If the original model is continuous in space and time, the equations you will have will be continuous in space and time. If the model is semi-discrete, then you will have a semi-discrete set of equations. And if the model is entirely discrete, you will have a discrete set of equations. And I want to say that the weak noise theory kind of preserves the type of space you work on. If you're discrete, you remain discrete, etc., etc. And a curiosity around this is that we know classical integrable systems have an extensive amount of quants of quantities. If you work on a lattice of size n, an integrable system can have n, even sometimes more than n, quants of quantities. And the large deviation rate function will be hidden in those quants of quantities. I don't really have an interpretation to why this is the case, but it's actually what happens in practice. I mentioned that this machinery of the field theory and the variational approach and the integrability works in the continuous case, the semi-discrete and the discrete case, but it's even more robust than that. Whether you're studying a scalar model or a matrix model, the same machinery will apply and you'll be able to obtain an integrable model that is scalar valued or vector valued or matrix valued. And finally, the other comment I want to make is that this kind of map between the original models and the weak noise theory is injective in the sense that we know all the models in the KPZ class converge to one another, and all those integrable models on the other side will converge to one another exactly in the same way. So the integrability is robust in the sense that it works for continuous semi-discrete, discrete, as well as scalar models or matrix models. I'll explain what I mean by this. And today I want to show you this whole machinery, actually on 3 models. I want to show you the whole machinery. Firstly, on the scalar strict-weak polymer. Then I'll preview how this also works for the matrix version of the strict-weak polymer. And finally, I'll show you how this machinery works for the continuous time. q-TASEP. And we'll see how in the rest of the talk how to derive the hydrodynamic equation, how to get their saddle points, how to describe the hydrodynamic equation using legs pairs, and I'll show you how the large deviation rate function will also look like. Okay, so let's start with the first model, strictly polymer. So the strict polymer was originally introduced by Corwin, Sepelainen, and Chen, and it basically describes the recursion on the partition sum of a polymer. So I have a polymer described by a partition function, the n of t lives on a discrete space. And the partition function verifies the following recursion. So z of n t plus 1 is equal to y n of t, z n of t plus c n minus 1t. We'll choose in the recursion the randomness term yn to be distributed as a gamma random variable. So all the y's are id gamma random variable. So the distribution will be gamma of k theta. So that's the PDF of y looks like y to the k minus 1 divided by gamma of k, theta of k, and exponential minus y divided by theta. And the characteristic function of the gamma random variable, which I will use later on, is the expectation value of exponential minus ys is 1 plus theta s to the minus k for s bigger than 1 over theta. In practice, on a lattice, the construction of the polymer would look like this. So I use the same representation as the mathematician, where I have t on the x-axis and n on the y-axis. So here I would have 0. I would start from the point 0, 1. And the polymer is allowed to move either to the right or in the diagonal until, let's say, final point Tn. And you have the randomness basically on the horizontal links, but not on the diagonal ones, because you have a 1 here. When you think of such recursion, you also have to think of an initial condition. And the initial condition I will mention today is actually a delta initial condition in discrete space. So I will choose the partition function at t equals 0 to be a delta function at a single site. For this problem, it has been obtained by the community that the expectation value of exponential minus u of z and t is a certain freedom determinant for a time t bigger or larger than n. This is a standard result. And when you start from such initial conditions, so when you fix the polymer to start at single sites, and when you observe only the partition function at one point at final time, you would call this the point-to-point polymer, because you just go from one point to another one. And in practice today, I'm going to focus on such type of observable where I only focus on one point on the final line. So this is my setting, the point-to-point polymer. And right now, I would like to actually reinterpret this generating function using field theory. So not using the freedom determinant, but using another form of representation. So let me call this observable now capital O of Z. My observable capital O of Z can also be expressed using kind of law of total expectation. So if I want to know the law at the final point, I can just condition on all the previous values until I go back to my initial condition. And in this case, I would like to say that the expectation of my observable is the expectation over all possible history of my partition function. So I would take the product of all the sites on my lattice. This is the physicist part. D of Z and T. I have to condition on all the realization of the randomness at every single site. So I also have the product Z and T of the measure of D, Y, and T. I have the constraint that the recursion of the polymer has to be verified at every single site on the lattice. So I have a delta function that Z of Z and T plus 1 minus Y and T Z and T minus Z and minus 1 T, and still my final observable. So this is how I would like to represent the expectation value of my observable. Sorry? You have to put the probability. Oh yeah, I forgot the probability times the density of Y. In order to go to progress a bit, I would like to represent this constraint that the recursion is verified in free space. So I'm going to introduce the so-called response field. So dz of nt, dy of nt, and I'm going to introduce another field, dz tilde of nt. I have, okay, on my free fields, I have the density of the y's. And in Fourier space, I'm going to rewrite my constraint as exponential of minus z tilde nt for the constraint at every single site, times my recursion, so z of n plus 1 minus y and t z and t minus z of n minus 1 t, and again I have my observable O of z. And I'm gonna combine all those terms to define an action that kind of describes the weight of a certain path among all the realizations. So I will call this object exponential of minus s of taking all the products over all and t as 0 hat of z tilde and y. So this will really be the weight of trajectory. It turns out that in the case of the Strict polymer, you can also calculate the marginal over y exactly using the characteristic function of the gamma in the variable, and I'm going to do this in a second. So the observable expectation value of z is the triple integral over all my fields that I recombine as dz, dy, dz tilde of exponential minus s hat 0 of z tilde and y. And if I'm able to actually compute the marginals over y, I'm going to rewrite this as dz tilde of exponential minus s naught of z tilde against my observable. Okay. In the present case, the action s naught hat of z tilde y is written as the sum of all space time points of the lattice of z tilde nt factor of z n t plus 1 minus y n t z n t minus z n minus 1 t minus the logarithm of the density of y. As you can see, when I exponentiate, I actually have a linear contribution in y in the exponential, so I can exactly use the characteristic function of the gamma variable, which brings me to the action in terms of the fields z and z tilde, written as the sum over all spacetime points, z tilde nt, factor of z n t plus 1 minus z n minus 1 t plus k times the logarithm of 1 minus theta z nt t tilde of nt. All right. So this representation of this expectation value is completely exact at this stage. There has been no approximation to try to construct the action S hat or S. And this is for me the basic representation I'm going to use to introduce the weak noise theory. So now that we have this complete description of the theory, let's deep dive into the weak noise theory actually. So going back to my gamma random variable, I know, for instance, using this parameterization that the expectation value of y is equal to k times theta, and the variance of y is equal to k times theta squared. Now you see if I choose theta to be as theta tilde over k, and I take k goes to infinity, I'm going to have an expectation value for y that is of order 1, but the variance now will go to 0. So I'm going to have a noise that is almost deterministic as the variance really shrinks. And so I'm going to choose the parameter theta to be scaled like this, as well as k goes to plus infinity to define the weak noise theory of my model. All right. So when you choose such a parameterization, what does it do for us? So first of all, we also choose in this regime u to be a capital gamma over, sorry, k times capital gamma. So when you do this and k goes to infinity, we hope that this expectation value will actually enjoy large deviation principle, which would be something like minus k times a certain large deviation function over the parameter lambda. So we hope that because we're going to choose u to be proportional to k, we will have a certain rate for the large deviation, which will be k. So this is what we observe from this expectation value, and let's see now how it looks like from this standpoint. From this standpoint, you see here that if you take theta to be theta tilde over k, and k goes to infinity, you might have a problem here. So you might wanna rescale one of the fields. Actually, if you rescale the field z tilde to be k times z tilde, you're gonna cancel the factor 1 over k here, and you're gonna have a factor k in front of here. But one should not forget that there's another factor k here. So in practice, when you do the rescaling, z tilde gives z tilde times k. You realize that the action S naught of z tilde becomes k times the sum over all the spacetime points, z tilde of nt. I'm superseding the notation z tilde here. Z n plus 1, nt plus 1 minus z n minus 1 t plus the logarithm of 1 minus z n t Z tilde NT. All right. So now K is in front of everyone in the action. So in principle, since I have a rate K here, and in my observable I also chose to have a rate K, if K goes to infinity, I could, in principle, only look at the saddle point of this action. I can only restrict to a single trajectory by looking at the derivatives of my action with respect to the field and the response field at every single space point. So when K goes to infinity, the action is dominated by its saddle point. By the saddle point, I can take the derivative of my action as naught of z tilde with respect to my field, for instance, z and t, and the derivative with respect to the response field as well. This is how you would obtain the equations. And when actually you do this, you'll realize that the saddle point system is governed by the following recursion. So you have a set of two equations. So you'd have a first equation, Zn at the saddle point t plus 1 is equal to Zn minus 1 of t plus theta tilde Z of nt divided by 1 minus theta tilde ZNT, Z tilde NT. And the second equation you would obtain for Z tilde is that Z tilde of n t minus 1 is equal to Z tilde of n plus 1 t plus theta tilde of tilde nt divided by the same factor as above, 1 minus theta tilde ZNT, Z tilde NT. So in the weak noise regime, the fields are almost deterministic, and they're actually for the main contribution following this nonlinear dynamics. And when you compare the original recursion to, let's say, the first equation of this nonlinear system, you would obtain, for instance, that the optimal noise reads as follows. 1 over the optimal noise is 1 over theta tilde minus ZNT d tilde NT. So let's say you're interested numerically to solve this system. If you wanted to reconstruct the optimal profile of the randomness, you would solely have to look at this formula. And in principle, this can be done. Numerically. Obviously, now that you have such a system, you may wonder, okay, but what are the initial conditions? What are the terminal conditions? Where should I see the physics of the observable? And like, where do I see the point-to-point polymer? So if you study again the point-to-point polymer, you would realize that the initial and terminal conditions for these systems are the following. You would have z of n at time 0 is the same delta function as before, delta of n1. And because of the nature of the observable, you would see that z tilde of n t minus 1, the final time minus 1, is also a Kronecker delta function minus capital lambda delta of n comma big N. If you try to see geometrically what this recursion looks like, sorry? I have the final time here. So when you look at the light tone coming from the definition of the dynamics, if you substitute the lattice in coordinates a and t, we said earlier that we have an initial condition for z that lies at 0, 1. And what's going to happen is fine. So it's this way. So I have the point here, t minus 1, and where the initial condition, the terminal condition for z tilde is defined. I have a line here, n equals to n equal to 1, n minus n equal to t minus 1, and here n equal t plus 1. So because of the light cone of the dynamics, so when you look at which side can be obtained from the previous sides, you see that the dynamics is only non-trivial in this within this region in space. So outside of this region in space, one of the two functions is 0 because of the causality or the light cone. And when one of the two functions is 0, you can actually see that dynamic is linear, so kind of trivial. So to have a non-trivial dynamics, you actually need to be in that space. And again, this is governed by the light cone of the dynamics of the original polymer. When you look at those equations, also they have a kind of symmetry. One of them seems to go forward in space and time, and the other one backwards. And this is kind of a general features of the system you have in this in the weak noise theory. So if we take a step back, we originally wanted to look at the expectation value of some observable in some weak noise regime. We described everything using some action. We showed that we could take a saddle point over this action. We obtain a certain system with certain initial and terminal condition. And now what? So in principle, you haven't finished your problem because you need to solve this system in some way to actually plug the solution back to this action and obtain the rate function. And frankly, looking like this, I would not be able to tell you how to solve the system. It's nonlinear. It's hard. Let's see here. So now the realization, as I was mentioning at the beginning, is that such a system is actually classically integrable in the sense that you have the existence of a lax pair. So for discrete systems, so discrete in both coordinates, I will define the lax integrability as follows. So for a discrete lattice with coordinates n and t, I will define a certain vector v that is indexed by two coordinates v of n and t that has two components. Let's say v1 of nt and v2 of nt. And I'm going to study the following linear problem of v. I'm going to define a recursion v n plus 1 of t equals a certain ln of t vn of t. So ln will be a 2x2 matrix. And vn t plus 1 is equal to another matrix unt vnt. So u again will be a 2x2 matrix. So let's say I have an auxiliary problem defined this way, and I want to study the compatibility of the system. So the compatibility in this case means that if I start from coordinates nt, and I want to go up to coordinate n plus 1, t plus 1, I have two possibilities to do so. Either I can increase the n coordinate by 1 by applying L and t, and I would arrive at n plus 1 t. And then I want to go to n plus 1 t plus 1. And to do so, I would actually apply the matrix un plus 1 t. Now, if I want to choose the other path and go through nt plus 1 first, I would apply the matrix unt and then the L matrix L and t plus 1. And if you think that the two trajectories are supposed to be compatible and equivalent, this gives you actually constraints over the matrices L and U. And the constraint is actually that L and t plus 1 U and t equals U1 plus 1 LNT. And now you may wonder, what's the whole deal? Why am I introducing this and what's the relation to that? So it turns out I can actually construct two matrices, and I will show you those matrices in a second. L and U, there are 2 by 2 matrices. They will depend on the functions z and z tilde at nt and another parameter lambda, which is a spectral or Fourier parameter, such that this condition is verified if and only if this system is verified. So there's an equivalence between the two. And if such matrices exist, then you call them Lax matrices for the classical integrability. So it turns out this system is integrable in the Lax sense, and I will give you right now the Lax pair associated to it. So the matrix L in the case of the strict-weak polymer reads L and T is equal to matrix 1, 0 minus theta tilde Z tilde n T minus 1, 1. I will choose 1 over lambda 0, 0, and 1, 0, 1 Z and T. I could combine all the matrices together, but actually I like to have this kind of as a product where I separate the fields Z tilde and Z. And I chose this matrix so that its determinant is actually 1. And the matrix U of NT is equal to 1, 0, 1 minus Z and minus 1 T square root of theta plus lambda squared, 0, 0, 1 over square root of theta tilde, plus lambda squared times 1, 1, 0, theta tilde, Z and Z tilde nt. So you can actually compute explicitly this equation introducing the equations I've just given you, and you'll see that this equation is verified if and only if this system is verified. Now that we have actually access to those matrices and the problem over V becomes a linear problem, you can apply the inverse and direct scattering approach to actually solve the system exactly. And long story short, because I want to focus on the rest of my presentation, when you actually compute the scattering or when you look at the asymptotic expansion of the freedom determinant related to this geometry, you would find that the related rate function for the problem, psi of lambda, is equal to minus the integral over circle positively oriented around 0 of dv over 2I pi of the logarithm of minus lambda v to the minus n 1 plus v to the t theta tilde of 1 minus n plus t. From the scattering standpoint, you would try to solve this system at t equal to 1, t equal to 0, look at the points of quantity, and actually you would be able to see that the rate function is hidden in the points of quantity and actually looks like this. And so just to comment a second on the expression for the large deviation rate function, for all the models in the KPZ class, you always have a d-logarithm. And actually the argument of the d-logarithm usually looks like a propagator of a linear theory. So let's say if you were to forget about the nonlinear term and you add the same initial condition, you would basically find this type of propagator. Okay. It's actually running short on time. So I just presented you what happened in the case of the scalar strict-weak polymer, and I want to show you that all the construction I've just given you is actually robust in higher settings. So there has been a number of extensions of the strict-weak polymer, and one of the extensions is the matrix strict-weak polymer that was introduced by Arista, BC, and O'Connell. So the idea is that you would lift the recursion I originally introduced to you by having a recursion on the space of positive matrices instead of scalar partition functions. So for the matrix strict weak. The recursion is defined as follows. You have basically the same recursion z of nt plus 1 equal to square root of z of nt y of nt and square root z of nt plus z of n minus 1 t. The randomness y that appear here that replaces the gamma distribution is actually a Wishart random matrix. So the y's are IID Wishart matrices. When you work in the space of positive matrices, you can't just define the products z and y because otherwise it would not be symmetric. So to define the product between the Wishart matrix and your original partition function, you would have either the choice where you have the square root of z behind y, or you would have the square root of y and a z in between. And it turns out the model of interest in this case is the recursion where you have the Wishart and the square root of the previous partition function on each side.
Why is it the model of interest?
Sorry?
Why is it the model of interest?
It's a natural extension of the strict weak. It's integrable. It converges to a matrix version of the O'Connell polymer, and there's a number of open questions there. So you could also define a matrix log gamma polymer, for instance. The interesting questions would be similar. And you can also define a weak noise theory. And as I'll briefly mention, you can also define this nonlinear system and the Lax pair. And the Lax pair, instead of being 2 by 2, if you think that the matrices here are d times d, you would have a Lax pair that is of size 2 by 2, but each block would be a d by d matrix. So this whole machinery extends.
But my question is, if you change the product and you take square root y, z square root y, at some point something would fail in what you want to do?
Yeah, the calculation runs smoothly for this formulation. For the other formulation, the equations do not close that easily. Maybe there's another way to do it, but maybe I haven't tried hard enough. But Neil in his paper actually describes the both polymers, both configurations.
What are the parameters of a Wishart matrix?
Sure. So in this case, I would define the distribution of the Wishart as 1 over gamma d alpha, determinant of y to the alpha exponential minus trace of y, and I would have the measure over the positive symmetric matrices. So the measure mu of dy would be equal to the determinant of y to the power minus d plus 1 over 2 times the Lebesgue measure on all the coefficients of dy. I use the standard measure for the Wishart, but I introduce the parameters in this way. Right. And long story short, you can actually replicate everything I've done previously, and it turns out that the constraints you have by having the dynamics at every single space-time point. So if you have a delta function, let's say of z and t plus 1 minus square root of z and t, y and t, square root of z and t, minus z and minus 1t, you would rewrite this as an integral over a response matrix now, d z tilde nt, which lives in the dual space of z, and you would have the exponential of minus the trace of z tilde nt against your constraints here. And replicating what I've done so far, you would see that the nonlinear system you would obtain in that case is Zn t plus 1 equal to Znt factor the identity minus of size d minus z tilde z hat z tilde sorry nt Znt minus 1 plus Zn minus 1 t. And for the response matrix, we would have Zn t minus 1 z tilde nt identity minus Znt z tilde nt inverse z tilde n plus 1t. So the system you would obtain in the matrix case looks really similar to the system you have in the scalar case. And actually this system is also integrable in the Lax sense. You would choose the same Lax matrices and replace the scalar quantity by matrices. So you'd have some kind of block Lax matrix, and all the properties I mentioned to you still hold. So this is really robust because this is not only overfitted to the scalar case, but it also works in higher settings. All right. I only have, let's say 15 minutes at most. Okay. Won't necessarily have time to go everything. Okay, let me jump to the questions. So in the rest of my presentation, because I've been really ambitious, I thought I could also present to you the q-TASEP. So what are the difference between the q-TASEP and the strict polymer is that the q-TASEP is continuous in space, in time, sorry, and distance in space. So I wanted to show you that you could replicate the same machinery using a semi-discrete model. In the q-TASEP, you don't have a white noise appearing, but you have a Poissonian noise. So I wanted to show you that it's Poisson noise. Maybe the main takeaway is that you can also apply this field theory, this MSR formalism also exists in the case of Poissonian noise. So that allows you to obtain some system of hydrodynamic equation. And if I had the time, I would have showed you that these hydrodynamic equations actually can converge to the hydrodynamic equations we obtain for the O'Connell-Ure polymer, which is a natural limit of the q-TASEP. So we know that q-TASEP converges to the O'Connell-Ure polymer. And what I want you to remember is that the weak noise theory of the q-TASEP converges with the exact same rules, exact same scaling. And to my knowledge, the Lax pair you obtain for the q-TASEP, or even the Lax pair you obtain for the street-weak polymer, were not written before in the literature. So those would provide a new family of classical integrable systems. And you could actually play this game for the whole KPZ hierarchy. You could look at the Q-Han models. You could look at the Q-push models. You could look at the Q-PNG. You could even look at vertex models. So what I want to tell you is that this is generic, and if you want to discuss, I'd be happy to pursue discussion. But for the few minutes that I still have, I want to mention a number of final remarks and open problems if you're interested in actually following this. So I want to say that the results for the 3-quick polymer and the log gamma have already been published. So for the q-TASEP, we're gonna write this in a couple of weeks. So the results exist, but they haven't been published yet. But if you want to know more, at least about on the polymer side, this is already out. So on the kind of open problems I want to mention to you. When I introduced the next pair, I've told you that you have to solve the scattering problem exactly if you want to go back to the large deviation rate function. So if you take the weakness theory of KPZ, the scattering has been solved on the full line on R, but no one has been able to solve the scattering problem on the half line where you have a boundary condition like a Neumann boundary condition or Robin boundary condition or Dirichlet. So the scattering solved in full space. But not in a half space. The second open problem I want to mention to you is that we've done this work for the European polymer, the KPZ equation, q-TASEP, continuous in time, and also discrete in time. The 3-quick polymer, log gamma polymer, but there are still zillions of models in the class. So obtaining the lax pair for the rest of the models is an open problem. The third open problem I want to mention to you is that there's been some work, notably by Tamara Grava and Guido Mazzucca, about the relation between the equilibrium measure of classical integrable system and matrix ensembles. Notably, so let's say Grava and Mazzucca, they've been, for instance, able to relate the equilibrium measure of the Toga lattice to the Gaussian ensemble. They've been able to relate, for instance, the Volterra lattice to the antisymmetric Gaussian ensemble. And they've also worked on the exponential Toda lattice, on the defocusing Schur flow and the defocusing Ablovitz-Sladik flow. It would be interesting to relate the equilibrium measure of the lax pairs of the weakness theory of the KPZ class to other matrix ensembles. That could be really interesting. Most of the study that has been done on a lattice or for a discrete space. But when you go to a continuous space, obviously those matrix ensembles would correspond to some operator. And I think it would be interesting to characterize this operator. So the open problem is equilibrium measure. Of the classical integrable system that appear within KPZ. When you study those classical integrable systems, it turns out that all the initial conditions are in practice deterministic. Even though the initial condition for the polymer or the particle model can be random, the randomness is actually squeezed with the same rate as the large deviations, and the initial condition become deterministic. That would be interesting to actually study those classical integrable model that appear in the KPZ class with random initial condition and see if this brings new knowledge back to KPZ. random. The fifth open problem I want to mention to you is something that Percy Dive told me about in MSRI a couple of years ago. So it turns out that the classical integrable models are also related to algorithms that appear in computational linear algebra. Notably, the flow of the total lattice corresponds at integer time to the QR algorithm to diagonalize matrices. And it would be interesting to understand which type of algorithms can come from the flow of the classical systems coming from the KPZ class. I think this hasn't been studied neither. So linear algebra. Coming from the flow of the integrable systems in KPZ. And finally, something a bit small blue sky, but there's been a number of work, notably by Benjamin Doyon and Yoshimura on TT bar deformations of classical integrable systems that keep the final system classically integrable. That might be interesting to study the TT bar deformations of the classical integrable systems you obtain within KPZ and see if they correspond to something and see if there's some interesting property you could get out of it. This also is an open problem. And on those 6 open problems, I'd like to stop here and take a few questions from the audience.
This integrable systems related to the strict weak polymer model. So how should I think of it? Is a generalization of what non-integrable system?
So in the zoo of KPZ, so the strict weak polymer does converge to O'Connell-Ure, and the weak noise theory of O'Connell-Ure is related to the discrete self-trapping model, which is a generalization of TODA.
Okay, so basically it's a generalization of TODA. And but then you say that also in the Wishart model, no, what is it called? The matrix.
The matrix strict weak polymer, yeah.
So I should think of this matrix, so this integrable system arising from the matrix model as some sort of a matrix solitonic system.
Yeah, somehow, yes, you could. If you take the books on integrability from Ablowitz and his collaborators, he actually studies the AKNS system like the KDV or the nonlinear Schrödinger using having a vector representation or a matrix representation. So the equations and the integrability not only stands for the scalar model, but also for the matrix model. And at least the scattering theory of the matrix model has been studied in the case of NLS. So it's not that much of a surprise that you could discretize those matrix models as well.
So in your arguments, you have a Z, which is the original log gamma or strict weak field, and then you have a Z tilde, which I could think of as like a Lagrange multiplier, basically, right? Yeah. It seems almost like a miracle. I mean, these are very asymmetric in the way they appear in your formalism, right? Like one is a Lagrange multiplier and one is a probabilistic object. It seems almost like a miracle that when you do the saddle point analysis, they suddenly become symmetric. Do you have some kind of explanation, or is this like obvious to you in any way?
So in the case of the strict weak, that was completely trivial and straightforward that the equations were symmetric, right? That you could symmetrize it. In the case of the q-TASEP, which I didn't have the time to actually develop entirely, the original response field has a dynamic that is totally different from the one of the regular partition function. So you have to find a clever change.
The response field being the Lagrange multiplier.
Yeah, the Lagrange multiplier has a dynamic that is totally different. But if you find a clever change of variable, then you can have dynamics that is symmetric between the transform Lagrange multiplier and the original partition function.
And if you kind of go back, let's say you take a situation in which like q-TASEP in which that transformation is non-trivial. If you go back to the original stochastic dynamic, this will correspond to some different Lagrange multiplier, presumably, like some transformed Lagrange multiplier. Do you have some interpretation of that probabilistically?
No, that would be really interesting. So in our case, we can kind of discard all the difficulties in the sense that when you do a change of variable, you're supposed to have a Jacobian between the fields. But because we work in this large deviation regime, the contribution of the Jacobian will just, they will never appear. So we totally discard that. But if you wanted to do it the probabilistic way, you need to take into account all the Jacobians appearing, and you might have different terms appearing in your dynamics. That would be fascinating to see. So this non-trivial change of variable appeared in the context of the q-TASEP, but also for the weakly asymmetric exclusion process, we have the exact same problem. We had to find a clever change of variable to make things symmetric. And also, if we think of another system, KPZ, you have two ways to do the weak noise in KPZ. Either you can do it directly on the KPZ equation, or you could do it on the stochastic heat equation. And actually, if you take the Lagrange multiplier of KPZ, you see that the equations are really not symmetric. But if you take the Lagrange multiplier of the stochastic heat equation, the dynamics are completely symmetric between the original partition function and the Lagrange multiplier. So there may be a change of variable in the differential equation that makes things look nicer.
Thank you. Is this change of variable always the sort of Kolov transform?
Could be even more complicated in collapse. So, and I mean, I can at least show you how it looks like for q-TASEP. So for q-TASEP, yeah, if you have an original Lagrange multiplier or response field, which I would call z tilde n, the change of variable that brings you to dynamics that is really symmetric is the map from z tilde to yn, such that 1 plus yn zn being the q to the power, the position of the nth particle in the q-TASEP, being equal to exponential minus zn z tilde n. So the original Lagrange multiplier would be z tilde, and actually I need this y to make the dynamics being symmetric. So it's a non-trivial one. And there's no general rule, I would say, when you go from q-TASEP to the weakly asymmetric exclusion process or even the beta polymer, there's no general rule that tells you, oh, you have to do this change of variable. So at the moment, we've been able to obtain this lax pair for KPZ, O'Connell-Yor, log gamma, the Strickwick polymer, the q-TASEP in continuous time and discrete time. But for instance, for the beta polymer, I know how to write the system. I just have no clue how to get the lax pair. I really have to eyeball it and brute force it.
Further questions? Let's thank Alexandre again.